Hello, Honors Chem students. This is Mr. Tro, and I'm going to be bringing you the first installment, part one of the Unit 11 notes. Unit 11 is about acids and bases, probably one of the most widely studied topics in all of chemistry. It's actually a really fun unit to do in person, but we're going to have to do it remotely. So apologize in advance for not having as many activities to do as we would have done in regular class, but we're still going to go through and try to teach you as much about them as we can. So this part one notes, you can find the blank PDF notes in Schoology, and you feel free to follow along either on your iPad or on paper if you choose to do it that way. Okay. In this first set of notes, we're going to just basically introduce what acids and bases are, talk about their definitions and how we identify them. And then we're also going to talk about how we measure how strong they are, which is something called pH. Okay, so let's jump right into it. First of all, if you look at this list here, you can see that acids and bases have properties associated with them. And if you look closely, you see that they're pretty much opposites of each other, right? So if we talk about an acid, right, talk about an acid and a base, I'm going to use red to describe acids and bases, blue to describe bases, because you'll see in a little bit later, those are typically the colors that they make when we use indicators to determine whether something's acidic or basic. So if you notice, acids usually taste sour and bases taste bitter. You know this because lemon juice is considered an acid. Citric acid is a very common acid, and if you've ever bitten into a lemon, right, you know that it's very sour. Bases taste bitter. Maybe not the best example, but soap, for example, lye would be considered a base. And if you've ever had a parent who maybe wanted to teach you a lesson and put a bar of soap in your mouth, I know I did growing up. They definitely taste bitter. Okay, but if you go through this, you're going to see that they have pretty much opposite properties. We'll talk more about indicators later, but acids will turn blue litmus paper to red, whereas bases will turn red litmus paper to blue. So think blue for a base, B for base. Acids, if you put them on many metals will actually, people say that acids dissolve them. They don't actually dissolve them, but acids will react with metal. They'll corrode the metal and they'll kind of quote unquote eat through it. Bases don't do that though, so that's an important thing. Um, both of them will burn you if you get them on your skin if they're strong enough. Um, Bases tend to be slippery. It's one of the ways you know you're dealing with a base. Next time you help clean the house and you use ammonia, which is a base, you can feel it in your fingers. It's very slippery. And then lastly, they're both considered to be electrolytes. And what that means, from if you remember from earlier, that means that they conduct electricity. Okay. And we'll see why in a little bit. But basically, no pun intended, acids and bases, they produce ions in solution. And so those ions help conduct electricity. Okay, so those are the general properties. Just know them and know that they're pretty much opposites of each other. Now, there was a long-standing definition for acids and bases. We call it the Arrhenius definition. It's not totally true, but we still like to talk about it in generality because it was the working definition for quite some time. But basically, the Arrhenius definition, and we're not going to spend a ton of time on this, but it says that acids will form hydrogen ions in water. Okay, that's what acids do. Bases form hydroxide ions. Now, you are probably familiar with the hydroxide ion. You've seen this ion before from a polyatomic ion sheet in the back of your periodic table. We, however, don't see this. And there's a reason for that. The reason for that is that this is just a proton. If you think about it, think about hydrogen. Hydrogen's one proton. Usually there's no neutrons in the nucleus and has one electron. So if you're H plus ion, you have lost an electron. You're essentially just a proton. And protons don't just exist on their own. They don't just float around on their own. So this definition doesn't really hold up because it requires acids and bases to be done to exist in water-based solutions. Okay, it limits acids and bases to only water-based solutions, and the reason why is that a proton doesn't really exist on its own. What this really means is that the proton, right, attaches to, say, a water molecule, and that creates what we call hydronium, which is H3O plus. Okay, but you have to be in water for that to happen, and so we don't really use this definition anymore for that reason. And also, if you notice, it requires that these acids and bases disassociate, which means they break apart into their ions. And we know that there are many acids and bases that are not ionic. There are ones that are covalently bonded. So this definition doesn't hold up in those cases. So this is not our working definition. It's just an intro. Okay. The working definition we are going to go with is the Bronsted-Lowry definition. So this is the important one. And it dictates what an acid and a base is based upon how they react in solution. They don't have to be in water for it to occur. They just have to be reacting with something else. Okay, so we say that acids are proton donors. Donors, right? Meaning they give. They give H plus. Okay. For the rest of this unit, when you hear someone talk about H plus, we're talking about a proton. Okay, as I explained earlier. So if you look here, if we were to put, for example, hydrochloric acid, HCl, into water, because HCl is an acid by definition, it is going to donate its proton, right? So it's going to take the H plus and it's going to donate it over to the water. And if you look here, you see that that creates water, which was neutral, now receives a hydrogen plus ion. So now it's H3O with a positive charge. It leaves behind the chlorine, which is now going to be just a negative ion in solution. Okay, and you see the negative right there. If you look at the total charge on the left side, it's neutral. If you look at the total charge on the right side, it's +1 and -1. It's still neutral. So we always conserve our charge in these reactions. But this, the hydronium ion, this is what makes something an acid. Okay, that. This is the characteristic ion of acidic solutions, of acids. Okay, and that's very important. So if a solution has a bunch of hydronium ion floating around in it, it's going to be acidic. Okay. Now, since acids are proton donors, and I told you that acids and bases are essentially our opposites of each other, that means that bases are going to be proton acceptors. Okay. So they will receive a proton from something else in solution. So if we look at this example down here now, right, we have a phosphate ion in solution, PO4 3-, and it's in water. Now the phosphate ion, since it's a base, okay, it's going to act like a base, which means it's going to accept. So it's basically going to go up to the water and say, "Hey, water, I'm a base. I want hydrogen ions," and water will say, "Okay, I will donate an H plus over to you." So you see there, the arrow is the opposite direction. The arrow is now going to the PO4. It's receiving it, and that makes this HPO4 2-. It was -3, now it's -2. And that's not really the most important thing that's created. The most important thing that's created here is the OH- that's left behind from the water. If you think about it, right, water is just HOH, and if you were to get rid of one of the H's, right, you now have an OH- ion. Okay, so this right here, that's the important thing. That's what we call hydroxide ion. Okay, and that is, you guessed it, the characteristic ion of bases. Okay, so if a solution has a ton of OH- hydroxide floating around, it's going to be a base. Now, in true transparency, solutions that are acids and bases, they have both actually. They'll always have a little bit of H3O plus and a little bit of OH-. It's just a matter of which one has more. Okay, we'll talk about that a little more later. But if your H3O plus is in greater supply, you're an acid. If OH- is in greater supply, you're a base. Okay, so that's the basic definition there. There's a little diagram here which we're not going to get too deep into, but you can see, right, that if this truly is an acid, that it is donating H plus to the base. The thing that's paired with the acid, because by definition, since it's accepting the proton, it's by definition acting like a base. Okay, it's being forced to act like a base. And that would be the forward reaction. So if we're just thinking about the forward reaction here, that's what we're looking at. But what you need to understand is we just spent a whole unit talking about equilibrium, and equilibrium reactions go two ways, right? So if we look at the reverse reaction now, what was created, right? The thing that was created, which is the A that's left behind with a negative charge, and now the HB plus, which was created, those can also go backwards, right? And we're not going to get into what these are. These are called conjugates. We're not going to get into that. We decided to remove that from the remote learning process. So if you want to talk about conjugate acid-base pairs, we can, and I'd be happy. Your teacher would be happy to do that. But for this unit and this year, we are not going to go into those. But I just wanted to show you that there's a forward reaction that creates new substances, but those new substances can still go in a backwards reaction, and these reactions can still come to equilibrium. Okay. So this is just a little recap of the last slide or the previous slide. And so it's stuff we've already learned, but hydronium, H3O plus, right? That is the characteristic ion of an acidic solution. So it's important to understand, right, that in an acid solution, there will always be more hydronium than hydroxide. Okay. Hydroxide is the characteristic ion of basic solutions, right? So there will always be more hydroxide in a basic solution. Now, if you are familiar with acids and bases, maybe from middle school or just you've heard about them, you understand that acids and bases, they might be opposites, but there are many things in the world that are not acidic and basic, right? And we refer to those solutions, those mixtures, as neutral. Okay, so this is the first time we're talking about neutral, but as logic would have it, right, neutral refers to these being equal to each other. So pure water, for example, is considered neutral. So what you see down here is a representation of pure water, right? If we had one water molecule and another water molecule, now you never have a sample of just two water molecules. If you had a glass of water, you'd have trillions upon trillions upon trillions of water molecules. However, right, if we have these two water molecules, what they can do is a small portion of them will actually come into contact with each other, and we will transfer over an H plus. So sometimes a water molecule will act like an acid, and sometimes it'll act like a base, and one will accept and become H3O plus, and one will donate and become OH minus, right? But if you notice, think about the ratios here. Think about the ratios. This is in a 1-to-1 ratio, right? Which means if you create hydronium, you also create hydroxide. So in pure water, even though this process is happening, the water is still going to be neutral because every time you get a hydronium, you get a hydroxide that's going to completely cancel it out, okay, in terms of acid and base strength. Okay, we'll talk more about that later. And a couple more things about it. We have been talking about that all acids donate a proton, and we've always said they donate a proton. And in every reaction that an acid undergoes, it will donate one single proton. But that doesn't mean that that's all it can do. There are some acids that have the ability to donate more than one proton, and we call those either di or triprotic acids. So we have some terminology here. They're referring to acids that can donate 1, 2, or 3 protons. We're going to use the prefixes you're used to, mono, di, and tri, to indicate if one hydrogen is donated, or 2 hydrogens are donated, or if 3 hydrogens can be donated. The protic part, monoprotic, refers to proton, which is the H plus. Okay, that refers to the H plus. So we're just going to go through a couple examples here. And the first example is HNO3. This is nitric acid. All these examples we're going to go through, we're going to assume that these substances are placed into water. So if nitric acid was placed into water, I'm just going to use a solid arrow. What will happen, because nitric acid is an acid, by definition, it's going to donate its H plus over to the water. Now, what that creates, well, what it leaves behind, first of all, is just NO3, which now has a negative charge because it lost a positive charge. So it's left as the net charge is -1. And it creates water with an extra H on it, so that's H3O plus. Now that should be familiar to you. That is the hydronium ion. Okay. Now at this point, there is nothing left over. There is nothing left over on that nitrate ion, the NO3 minus. It has no H to donate. So it's done. And it ends its life at that point right there. So that's a monoprotic acid. That's pretty much what we've been talking about. If you have a diprotic acid, the scene changes a little bit. And if you think about this, right, if you put this with water, it's going to do the exact same thing. Okay, it's going to do the exact same thing. The I'm going to use a double arrow here. It's not super important right now that you understand why I'm doing that, but I'm going to, so it's accurate. The H2SO4, right? The H2SO4, scratch that. I'm not using a double arrow yet. I misspoke. I'm going to use a single arrow right now. Okay, but the H2SO4 will react as an acid, but only one of the H's can be donated at any one given time. So after that happens, think about this now. What's left behind is just HSO4. It was neutral, so now it's -1. And the water, just like before, becomes a hydronium. Okay. The difference, though, and I'm going to move this arrow to above just so we have some more space. The difference now is that this HSO4, if you look at the way it's structured, it has an H out in front of it. And so it can actually function as an acid itself, right? So if we were to picture now this HSO4 is floating around in the same solution, it's going to meet another fresh water molecule that hasn't reacted yet. So if it meets another fresh water molecule, it has the ability now to also donate that second H. Okay. And we go right down the line now. What's left behind is SO4, which you guys should recognize as sulfate ion. And then you get another H3O plus. Now I'm going to draw this reaction with a double arrow right here. And we're not going to, one of the topics we cut out of this unit is the idea of strong acids versus weak acids. Okay, sulfuric acid, this guy right here, he's a strong acid, which means when he reacts, right, when he reacts, he goes 100%, he reacts 100%, and there's no reverse reaction. So there's no chance for equilibrium there. But HSO4 minus, that is not considered to be a strong acid. So when it reacts, it actually doesn't react all the way, and therefore the reverse reaction can happen. And so this second reaction will actually reach an equilibrium. But we have decided to take the equilibrium component out of acids and bases because of lack of time. So if you see me draw a double arrow and a single arrow together, it's not a super important concept right now, but I'm sure your teacher would be happy to go into it with you if you ask. Okay, moving on. The triprotic, I'm going to go through this a little faster, but it's going to do the exact same thing, but it's just going to do it 3 times. Okay, so when this happens, right, you get H2PO4, which is just minus, and you get H3O plus. Okay, but if you see that H2PO4, it also has the ability to find another fresh water molecule, and it can undergo and donate and leave behind HPO4. Now, since it lost another positive charge, it's now -2, and it creates yet another hydronium. And this HPO4 ion can still go through another Bronsted-Lowry reaction where it donates a hydronium and leaves behind phosphate. Okay. and another H3O plus. It's important for you to realize, though, that with these reactions, okay, when you get to a second step or get to a third step, second and third iterations of these reactions are not nearly as strong as the first reaction. The first reaction will happen much more fully. Like this reaction happens much more completely than that reaction would. Okay, so just keep that in mind. But that's mono, di, tri, and triprotic. And then the last topic, really quickly, is the concept that um, you've seen in some examples. You've seen, let me go back really quickly um, to here. Right, if you notice in this example, water right here is getting hydronium donated to it. So it actually kind of acts like a base. It's being forced to act like a base. Water in this example is doing the donating. So it's actually being forced to act like an acid. There are some substances, water being one of them, but there are some substances that can act as either an acid or a base. So we call them amphoteric. Or they're capable of functioning as either an acid or a base, depending on the environment they're placed in. Okay, so they kind of get what we call peer pressure. Okay, they get peer pressure from another substance. If they're in the presence of another substance that's an acid or a base, these substances that are amphoteric can be forced to act a certain way. Okay, water is probably the most common. We've talked about this reaction already where you have pure water. Some of it gets donated or some of it gets ionized into H3O plus and OH minus. But looking at this example right here, bicarbonate ion, this guy, HCO3 minus, if he's placed into an environment with a hydroxide, for example, so if he's placed in with an OH minus, if you look, what does bicarbonate become? Well, bicarbonate becomes CO3, right? So to go from here over to here, by definition, the bicarbonate had to lose its H plus. And so the definition, the bicarbonate actually acts like an acid because it donates its H plus. But if you look in the second example, bicarbonate becomes H2CO3, which means in this case the bicarbonate actually accepted, right? It actually accepted the H plus, so it acts as a base. And those are called amphoteric substances. And there's a picture in your notes that will explain that. Okay, so that is the introduction to acid and base terminology and properties. The next topic in this lesson is pH and pOH. This is the last and final topic in lesson 1. Okay, so we have a scale in chemistry, in acids and bases. We have a scale that dictates to us how strong or how weak an acid or base is. Now, I hesitate in using the word strength. If we were doing a full unit, we would explain a little more fully what acid strength is. But bottom line is an acid is considered strong if it has a really high amount of hydronium, H3O plus. A base is considered very strong if it has a really high concentration of OH minus, hydroxide. Um, but we have things that are strong acids, like hydrochloric acid, the same stuff that's in your stomach. That's a very strong acid. But we can make a very dilute solution of hydrochloric acid, and you wouldn't consider that to be strong, quote unquote strong. So the term strong is kind of a weird term. We're going to use it loosely here in this remote learning situation, but it does mean various things. But pH and pOH, pH is a measure of how strong an acidic solution is. pOH is a measure of how strong a basic solution is. So if you look, right, you have the H and you have the OH. You have the H plus and you have the OH minus component. Okay. But it's just given a numerical value to the strength of acids and bases. Okay. pH deals with the hydronium ion, okay, H3O plus. pOH deals with hydroxide. So we have a scale, right? We have a scale, and I'm just going to draw kind of an arrow timeline, if you will, or a trend line down here. If we're talking about pH, right, you can have a pH of 0, you can have a pH of 7, and you can have a pH of roughly 14. Now, there are cases where it goes a little below 0 into the negative, and there are cases where it goes a little above 14. But for the most part, the pH scale has 14 values on it. Okay. If you are at 7, if you have a pH of 7, you're right in the middle, we say that you are neutral. Okay, so that should make sense. Right in the middle of the pH scale, we have neutral solutions. If you are all the way at 0, you say you're at 0 or 1 or 2, okay, we would call you an acid. We would say that you are a strong acid. Okay, so the lower the pH value, the stronger it is as an acid. Now, if you look on the other side of neutral, we should have base, right? So if you are at the 14, we say you are a strong base. But understand that it's a spectrum, okay? So you don't have to have a 14 pH to be a strong base. You could have a 12 or a 13 and still be considered a strong base. But as you move towards neutral, in both cases, you as a solution get weaker, right? So we would say over here we have what's considered a weak acid. And over here, we'd have what we consider a weak base. And it's this whole continuum of the pH scale, okay? So when we figure out what these values are, yes, less than 7 are acids, right? Greater than 7 are bases, and then neutral is equal to 7 or right around 7. But there's a whole contingency. So if I was a solution and I fell right about here, I'd be a very, very weak acid. If I fell over here, I'd be a very, very weak base. If I was here, I'd be a moderately weak base. If I was here, I'd be kind of on the verge of weak and strong. If I was over here, I'd be a very strong base. Okay, this would be a strong acid. This would be a moderately strong acid, very weak acid, and eventually neutral. Okay. Um, the pH scale is a logarithmic scale. It's an exponential scale. So it doesn't go in a linear fashion. 1 decimal point on the pH scale is a factor of 10 difference in strength. Okay, so that's important to understand. So if you notice the trend, right, the trend in terms of concentrations, right, when the concentration of hydroxide increases, that's molarity, the concentration of hydronium decreases. They're inverse with each other, right? So every time hydronium goes up, hydroxide goes down. These are inversely related. So this is important, right, to understand that these are inversely related to each other in every solution. In every solution, hydronium and hydroxide are inversely related. Now there is a slight typo in this chart, right? If you notice here, right, this should be -7th, -8th, and you can continue on if you want to adjust those. There's just a slight typo in the graphic. But if you look at, right, when the pH is 7, the concentrations are about equal between them. When the pH is, say, 1, if you notice, right, the strength of the acid ion is 1/10. The strength of the base ion is very, very, very small, right? It's to the trillionth. So, and then when we move to a pH of, say, 13, you see now the base concentration is much larger than the hydroxide is much larger than the hydronium. So it's just this interplay between the two, okay? But it's a logarithmic scale. This is obviously not in English, but looks French. If you notice, right, if we were to have a solution, this is the nice graphic because it shows that when it's neutral, you have about the same concentration of hydronium and hydroxide, okay? But if I had an acidic solution with a pH of, say, 1 or 2, you notice there's an exorbitantly higher amount of hydronium than there is hydroxide in that solution. Okay, so that might be a nice graphic for you. You should also notice that when the pH is 0, there's this thing called pOH, and it's 14. When the pOH is 0, the pH is 14. When it's 10, it's 4. When it's 4, it's 10. When it's 7, it's 7. You should notice, right, from this, that no matter what you do, pH plus pOH is going to equal 14. They are the opposites of each other. Okay, so you can always find pH and pOH. And if I had a pH of 3, well, 14 minus 3 is 11. That means my pOH would be 11. Okay, right? So we'll get more into that later. But here are your basic equations that you're going to use in this unit to describe pH. We told you that pH is logarithmic and pH is exponential, so it does deal with logs. Okay. The log button on your calculator can be found right left of the number 7. Okay. It's not a natural log, it's a standard log base 10. So if you were given hydronium, so say you had the concentration, remember the brackets here mean molarity. So if you had the concentration of hydronium, you would use this equation. You'd do negative log of the concentration, and it would give you a value for the pH, something between, right, 0 and 14. Okay. Now, if you've learned about logs in math class, you know that if you want, log is a way of getting rid of an exponent, which means if you look between these two, these two equations are solved in relationship to each other, right? So if I take pH, if I had pH to a certain power, you see that the log actually is a way of getting that variable out of the exponent. So the opposite of negative log of hydronium would be to find, if you wanted to find hydronium, you would have to take 10 to the and raise it to the power, right? So this is the power. That's an exponent power, okay? If I raised it to the negative is just a cosmetic. In both these cases, the negative sign is purely cosmetic so that our pH ends up being a positive value. But I raise it to the power, okay? And we'll do examples of using those. If you see here, this is pH, okay? When you have pOH, if you notice, they are the same exact equations, except, right? Except what's in the solution. So I'm actually going to use different colors here. I apologize for that. I'm going to use red. I'm going to use red for hydronium, and I'm going to use the blue for the hydroxide. Okay. I apologize for background noise. It's a garbage day where Mr. Tro lives, so they're coming through right now. All right, so if you notice, they're the exact identical equations. These two equations are identical except what you put in. Either if you're talking about pH, you put hydronium, H3O plus. I want to point out, right? I said it earlier, but every time you have H plus written, it really means H3O plus. H plus doesn't exist on its own. H plus is a shorthand way of describing hydronium. Okay, so you will see me when I do examples, I will always write H3O plus. But this is the shorthand method and it's totally fine. Just get used to that. So those are the same. And then like we talked about before, they always add up to 14, pH and pOH. With these 5 equations, you have the ability to convert to solve any pH problem you need to do. Okay, and so the next few slides have some examples. You might want to have your calculator out while we go through this so you can practice doing the calculations. Okay, so the water in a lake was found to have an H plus of 3.2 times 10 to the negative fifth. Find its pH. Okay, we can do that. So it wants to find pH. So going back to our equations, right? If I want to solve for pH, I need to know the hydronium concentration. Do I know it? I sure do. It gives it to me right here. So that's great, right? So this would just simply, right? pH is equal to negative log of the hydronium concentration, which is negative log of 3.2 times 10 to the negative fifth molar. Remember on your calculator, 3.2 times 10 to the negative fifth is 3.2 e, which is second comma, negative 5. So on the calculator, right, we go negative log. Remember, log is next to the 7. 3.2 times 10 to the negative fifth, and we got 4.49. 4.5 if you do sig figs. Okay? And that's going to make it acidic. Why? It's less than 7. Okay? So that's a slightly acidic lake. There's many reasons why a lake could be acidic. Most common reason is that it's near a volcanic vent, and sulfuric acid gets vented out as a gas and gets dissolved in it. But that's just a side note. The Des Plaines River, cool. Water measures a pH of 7.92. So right away, you could say to yourself, this is slightly basic. Okay, it's slightly basic. Okay. What is the H plus concentration? It should be a pretty small number if it's an H plus concentration. Now, if I want to solve for H plus, right? If I want to solve for H plus, if you look, I need to know the pH. I need to know the pH. This problem gives me the pH, which is nice. So it's just a one-step situation, right? So if I want to know the H3O plus concentration, I'm taking my pH, I'm taking the number 10, because these are all log base 10, to the negative pH. So I just got to plug that in my calculator. 10 to the negative 7.92. And I'm sure we all know how to do that. You use the little caret button, negative 7.92. And I get 1.20 times 10 to the negative eighth. And now since I'm solving for concentration, this is going to be molar. Okay. Now, it's worth pointing out, if you notice that this is a pretty small number, it's worth pointing out that in a neutral solution, the H3O plus equals the OH minus, right? Which equals 1.0 times 10 to the negative seventh molar. So if you have a neutral solution, all neutral solutions will have a hydronium concentration of 1 times 10 to the negative seventh and have a hydroxide concentration of 1 times 10 to the negative seventh. The reason I'm telling you that is because you can then glance at a number, like for example, this number right here, again, I apologize for the background noise, it's a garbage truck. This number right here, if you compare it to 1 times 10 to the negative seventh, it might not at first look like it, but this number is bigger. It's bigger than 1 times 10 to the negative seventh, which means the solution in problem 1 has a higher concentration of hydronium than it would in a neutral solution, which makes it acidic. This one, look at this. 10 to the negative eighth is smaller than 10 to the negative seventh, which means this solution has a smaller amount of hydronium than it would if it was neutral. Well, if you have less hydronium, that means you have less of the acid ion. That makes it basic. Okay, so it's kind of a quick way of looking at a solution and telling whether it's acidic or basic. Okay, moving on. I don't know why these are numbered the way they are. This should be 2. It must be an auto formatting issue. Apologize for that. Number 3, though, Coca-Cola. The drink has a hydronium concentration of that. Find the pH and the POH of Coke. Okay, so to find the pH is going to be pretty simple, pretty straightforward. Just like before, pH is negative log of H3O plus. Notice I'm always kind of writing my equation out so that it's clear what has to be plugged in. So that's negative log of 3.67 times 10 to the negative fourth. Because that number is greater than 10 to the negative seventh, we would expect that this would be acidic, right? It's a stronger amount or a larger amount. So let's pop this in the calculator. And we get 3.4, let's see, 3.44. Now I'm not going to round this yet, 3.435. I'm not going to round it yet, simply because I'm not done with the problem. That would be 3.44. But I'm going to use that number now to answer the second part of the question. The second part asks me, what is the POH? Remember that POH and pH always have to equal 14, right? So 14 minus the pH is going to give me my POH. So that's 14 minus 3.4353, right? So that's going to be 10.56 as my POH. Okay. I would have had 2 digits after the decimal in this answer, and so I can keep 2 digits after the decimal when I subtract. Okay. So this is 3.44. Okay. Very good. Sample number 4. Oh man, scary. Okay, sample number 4. Blood has a hydronium concentration of 4.6 times 10 to the negative 8th molar. Is the blood acidic, basic, or neutral? So, like I said before, you can actually answer this question quickly because this, right, is less than 1 times 10 to the negative 7th. So the quick answer would be, since the acid ion is smaller in concentration, this should be basic. Okay, it should be basic. But if you wanted to calculate it for sure, you just have to find the pH, right? So pH is negative log of 4.6 times 10 to the negative 8th. So negative log of 4.6 times 10 to the negative 8th gives me 7.34 or 7.3 pH, and that's going to tell me that it's slightly basic, right? Not much, but slightly. So there's 2 ways to answer that question. Okay, if you don't feel comfortable, if you don't understand the 10 to the negative 7th comparison, you don't need to use it. Okay. Solution of baking soda has a, now understand, right? Now we're talking about hydroxide, so this is very important, right? This is the basic ion. All the other examples so far have hydronium, hydronium, hydronium. So keep in mind, now we're in the world of base here. Is it acidic, basic, or neutral? Right, so understand, right, that that is greater than 1 times 10 to the negative 7th. So the quick way of saying whether it's acidic, basic, or neutral is, since the basic ion is in greater concentration, it should be basic. You want to prove it, right? If you go POH is the negative log of the hydronium, because that's what we have, right? Well, that's going to be negative log of 7.8 times 10 to the negative 6th. Negative log 7.8 10 to the negative 6th. That gives me 5.11 or 5.1, but that's POH. So don't be confused. Remember, less than 7 is an acid, but that's only on the pH scale, right? On the pH scale, if it was less than 7, like right here, it'd be an acid. On the POH scale, though, right, it's not the same. If it's right around 4, right, or between 4 and 7, it's going to be basic. So they're opposites. So this would be less than 7 on the pH scale. This makes it basic. Okay. Which is essentially what we said all together. Okay. Now the last one here um, uh, is probably not a problem that is going to be you'll be assessed on because we took strong and weak acids out of the picture for this unit, but it's kind of a stoichiometry or a ratio problem. Um, if you had this concentration of barium hydroxide is considered a strong base, which means it's going to react 100%. Understand that when that reacts, right, if you notice here, you have 2 hydroxides. Okay, so while the concentration of the base is 0.00035 molar, OH minus, you get two OH minuses for every one BaOH2, every one barium hydroxide. And what that means then, right, is that the OH minus concentration in the solution is not going to be 0.00035. It's going to be 2 times 0.00035, okay, or 0.0007 molar. Okay, with that in mind, we can answer the two questions, right? Find the POH and find the pH. Well, if this is the OH, then the first thing I should do is find the POH, right? So POH is negative log of the hydroxide concentration, right? Which is negative log of 0.0007. So let's just do that really quick. Negative log of 0.0007. 3.1549. 3.1549, right? Which is, in terms of sig figs, 3.2. The reason I write it all out, though, is because I'm going to use my unrounded number in the next part. Asking you what the pH is. So very simple, right? 14, they have to add up to 14. So 14 minus 3.1549. And you get 10.845. So I would have one digit after the decimal. So that's 10.8. Okay. Notice, right, that these two values will add up to 14. They have to. Okay. So that is an example. Those are examples of doing pH and POH calculations. In retro, these are the equations you'll use. Remember that acid and base, hydroxide and hydronium, are always inversely related. As one goes up, the other goes down in concentration. In a neutral solution, you're going to have equal amounts of them. Okay. Think of pH as being this spectrum of values where you can, it's a spectrum from strong to weak to neutral to weak to strong, all the way across the board. Okay. And then we went through some definitions. Amphoteric can be either an acid or a base. Mono, di, and triprotic donate 1, 2, or 3 protons. And then we went through definitions of our working definition for acids and bases, Bronsted-Lowry. That's the one we're going to go with. And then an initial definition, which was a little bit inaccurate and not as all-encompassing. And then the first thing we went over were general properties of acids and bases. Okay, so that's the concludes this video. The blank PDF is available to you. Like I said, we will also make the annotated version of this without the audio available to you as well. Okay, good luck, and I will see you again in Module 2.